Today we will be teaching you how to rewrite limit expressions into definite integral expressions. Limit expressions can be found using the 6-step Riemann-sum process to find area under the curve.
The 6-step Riemann-sum process is listed on the right side of the board. For example, if you have the graph f of x and you wanted to find the area under the curve from 0 to 2, you could use the Riemann-sum process to approximate the area of the rectangles under the curve.
The first step is to find delta x, which is equal to b minus a over n. B is the upper bound, a is the lower bound, and n is the number of rectangles under the bounded area.
The second step is to find c sub I. C sub I is equal to a plus I times delta x.
C sub I are the x values which you will plug into the original function to get the y values. Those y values will be the height of the rectangles. It is easier to use the right endpoints than the left endpoints because when using right endpoints, the heights of the rectangles are found using f of x sub I, while when using left endpoints, the heights are found using f of x sub I minus 1. Clearly, f of x sub I is a simpler expression to work with.
Step 3 is just to plug in c sub I into the function f of x. Step 4 is doing the sigma notation of f of c sub I. The sigma notation represents the total number of rectangles under the bounded curve. You get the height of all the rectangles in the bounded area.
In step 5, you multiply the heights by delta x, which is the width. This is because width times height equals the area of the rectangle.
The last step is to calculate the limit as n approaches infinity.
This is because as there are more rectangles under the bounded curve, the area of the rectangles gets closer to the actual area under the curve.
By doing this, you get the limit expression, which is what we want. Now that you have learned what a limit expression is, we can convert it into a definite integral. By analyzing your limit expression, you can see that the sigma of f of c sub I is equal to the sum of the heights, and delta x is equal to the width. So c sub I is equal to a plus I times delta x. So once you figure out what c sub I is, you can figure out what a is. And then after that, you can figure out what b is, because you know that delta x is equal to b minus a over n. So if you have delta x and you have the value of a, you're able to find the value of b. So now that you have your values of a and b and you know the original function, you can rewrite it as a definite integral. So that would have the integral sign, which means the area bounded by two values, a and b. So a is the lower bound, which is why it's on the bottom, and b is the upper bound, which is why it's on the top. And then you would have your original function right here, which is f of x, and then you would have dx, which is also equal to delta x. So you would have your original function times the width, which gives you the definite integral.
Now let's do some practice problems. The first example asks you to rewrite the expression as a definite integral. There are some components that you must find to be able to do this. You would need to find the values of a, b, and f of c sub I. From this expression, you can deduce that 5 plus 3i over n is equal to a plus I delta x. So you can deduce that a equals 5 and delta x equals 3 over n. You can also deduce that f of x is equal to sine of x because here the expression is equal to sine of c sub I. To find the value of b, you can use the given information about delta x. Delta x is equal to b minus a over n. So plugging in 5 for a, you would get that b minus 5 over n is equal to 3 over n, giving you b equals 8. To rewrite this as a definite integral, you would plug in a equals 5, b equals 8 of f of x, which is equal to sine x times dx.
In this second example, you're asked to rewrite this limit expression as a definite integral. By looking at the limit expression, you can see that delta x equals 1 over n, and c sub I is equal to I over n. You have to be careful not to include the 2 or the 3 into c sub I, because those are just parts of the original function. So once you know what c sub I is, you can figure out that c sub I is equal to a plus delta x times I. And delta x times I is just equal to I over n. So since c sub I is equal to I over n, you would have I over n is equal to a plus delta x times I, which is basically equal to I over n. So now you can figure out that a is just equal to 0. So now we want to figure out what the value of b is. So we have delta x is equal to b minus a over n. So 1 over n is equal to b minus a over n. If you plug in 0 as a, you can figure out that b equals 1. And by looking at this, we can figure out that the original function is equal to 2x plus 3. So now we want to rewrite it into a definite integral. So a is 0, which is the lower bound, b is 1, which is the upper bound, and then we have our original function, which is 2x plus 3 times dx, which is just the width of the rectangles.
In our last example, we have c sub I equal to 5 plus 3i over n, where a equals 5 and delta x equals 3 over n. We plug in 5 for a, giving us b equals 8. This is similar to our first example. However, in this example, we have 2 over n attached to this expression, giving us a problem. Normally, 2 over n would correspond to b minus a over n, which is also equal to delta x. However, in this case, delta x is equal to 3 over n, which is clearly not equal to 2 over n. What we want to do in this type of situation is change the 2 over n so that it is equal to 3 over n times a certain number, which in this case is 2/3. We rewrite the entire expression as this, giving us f of x equals 2/3 times x to the 4th. To write this as a definite integral, we create the integration sign, put a equals 5 as the lower bound, b equals 8 as the upper bound, and put f of x in the middle, which is 2/3 times x to the 4th times dx.